All right, so welcome to the lab on confidence and confidence intervals. Confidence intervals are just the range of values that are statistically kind of like unremarkable. What I mean by that is that it's the range that you would expect. So 95% of the data should fall within this range. Outside of those values, we say it's statistically significant. So the word significant in statistics and data analysis obviously means something really important. Saying that something is statistically significant means that we know that it's not just due to chance. But in order to understand that, we have to know what are the range of values that are due to chance. And in this lab, we're going to look at how we figure out those values and how we work with those values. So we're going to calculate the confidence interval of a sample manually, and then use the confidence interval to determine if a sample is representative of the population or if what we're looking at is a statistically significant difference. Okay, so we are going to call a new library. If you haven't loaded this library, go ahead and run install packages, but we're going to call the gmodels library. So if you haven't used gmodels before, do the install.packages, and then pass gmodels. But I have, and I'm not really connected to the internet. So, all right, that'll just give me an error. All right, so we're going to call library tidyverse. As usual, we are going to use the tidyverse. So I'll go ahead and run these. And we have loaded in our packages. We have our warning messages about which version they were built under. Not really a problem. Okay, so the first thing we are going to look at is we're going to generate some data. And this is a really useful technique in R because it allows you to create distributed data for modeling without having to collect it elsewhere. So every time there's like a hurricane or an epidemic or things like this, this is one part of creating those models. So generating data in this way is one component of creating these large, complex, and interdependent models. For more on the other components of like just the very basic building blocks, go ahead and check out the probability lab. Okay, so we're going to generate some data, and it's going to be body temp, and we're going to assign our variable body temp to our norm, and we're going to generate 10,000 samples, and we're going to generate data about body temperatures. Sorry, I forgot to mention that. And we're going to say that body temperatures are 97.82 on average with a standard deviation of 0.69. Everyone in our pretend world right here has been measured. So this is obviously not totally realistic in the real world. Normally you don't get to measure anything about everyone in the world. So what we're looking at here is we have set up a little pretend world where there are 10,000 individuals. The mean body temperature of those 10,000 individuals is 97.82, and the standard deviation is 0.62. Right? So we're going to load that little pretend world, our fake data about body temperatures, in there. Now we're going to glimpse and see what that looks like. So it looks like a series of numbers. It's 10,000 numbers. It's just a vector here. And every single measurement is in this series of numbers. So all we're doing is we're looking at one giant row of numbers that all come to a mean of 97.82 with a standard deviation of 0.62. I'm actually going to make it 0.69 because that is what's in the notes. I'll rerun that. We get slightly different numbers as we would expect because again, it's randomly generating these numbers per these specifications. Okay, let's make a histogram of it just to see how it looks when we visualize it. All right, and what we see here is a perfectly normally distributed range of numbers. We have the most popular numbers are, you know, right around 97.82. And then we see the bands as they go out. There are fewer and fewer, and out here we do have some outliers, but they're not extreme values. They are representative of our standard deviation of 0.69. Okay, so we're going to do one more thing. We're going to set a seed, and the reason we're going to set our seed is because we're going to take a randomly selected sample. And in order to do anything random and yet repeatable in R, you need to set the seed. You need to tell it exactly how you want things to be run randomly. It's pretty common to set the seed as 1, 2, 3, 4, so that's what we're going to set our seed as. Then we're going to take a body sample, and we are going to sample our body temperature. So we're going to pull out 10 random individuals from our population. So here is our population. It's these 10,000 individuals, and we are sampling 10 of those individuals. Okay? So we've pulled out 10 randomly selected people, semi-random since we set our seed here. Semi-random anyhow because computers. We're going to find the mean of our sample. What I mean by that comment is that computers actually can't do anything randomly. They can only do things that are pseudo-random, so they mimic random enough that it looks random and it generally can't be decoded by the end user, but not actually truly random for what random means. Okay, so we have our body sample. We're going to find the mean of our body sample, and the mean is 97.83. Now you might be saying to yourself, wait. The mean of our population is 97.82. You also might have gotten a slightly different number here. And you're saying, wait, 97.83, that's not the mean. Well, that is the mean of our sample of 10 people. So we only pulled out 10 people. It's not the entire population. And of these randomly chosen 10, we got a slightly higher overall mean, but pretty close. Okay, let's try this again with a whole lot more people. Let's try it with 100 people, okay? So I'm going to go body sample 100, and I'm going to sample from body temp 100 people, okay? So now I'm going to find the mean of my body sample 100. All right, now we're below. Yours might be slightly above, but again, we get a slightly different number. Usually it's closer to the overall mean, but not this time. Okay, we're gonna do it again with 1,000. Okay, now I'm getting lazy, so I'm just going to copy this block of code and add some zeros to it. Body sample 1,000, we're gonna pick 1,000 people, and we'll call the mean on body sample 1,000. Okay, we'll run this block, and we get 97.823. So the more people, the bigger the sample that we use, the more likely it'll be that we get something that is closer to the actual population mean. And this should intuitively make sense. I mean, you pick a greater proportion of the population, you're going to get a mean that's closer to the overall population, right? Okay, so it'd be really helpful if we could visualize these, right? So if you sampled 100 times, how often would it be high and how often would it be low, right? So now we're saying, okay, I'm going to take a sample, this time let's say 50. So I'm going to take a sample of 50 people 100 times. Of each of those 100 times I take a sample, how often is it going to be above 97.82, and how often will it be below 97.82? All right, so let's work that out now. First, we'll set a variable r sample, okay? And our sample will be just numbers, numeric. We're going to pass 100 because we have 100 samples that we want to take. And then we're going to say for I in 1 to 100, open curly braces, next line, a sample is going to be a sample from body temp, and we're going to take 50 records from our body temp sample, okay? And then our sample I is going to be the mean of a sample. All right, let's break this down just a little bit because it's actually kind of complicated. Excellent. Okay, so our sample, we've created a vector here of 100 numbers. It's just a 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, all the way up to 100. And then for every instance, so for 1, for 2, for 3, so every number from 1 to 100, a sample is going to be a sample from body temp. So this is the exact same code that we used up here. We picked 50 people from our universe of 10,000. And then we're going to say our sample number 1 is going to be the mean of our sample. So what we're doing is we have this vector that we're basically filling in at each position the mean from our sample. Okay, so we have 100 positions to fill in. First position, we take the mean of a sample. The second position, we take the mean of another set of 50 people. Third position, mean of another set of 50 people. Okay, let's go ahead and run all of this. Go ahead and run all of this. And now it would be really useful if we could make a histogram out of it. So we're going to call hist and then our sample. And then breaks, we're going to say breaks equals 50. Okay. So that actually does not look that great. So we have something that's somewhat normally distributed, but it's not very good, you know? We do have the most frequent up here and a couple down here, but you see that our frequency is really, really low. Okay, so 100 samples out of this is actually not even enough, even though that gives us 5,000, half of our population. So I'm going to copy this, all of this code, and I'm going to paste it down here, and I'm going to say, okay, rather than giving me 100 samples, give me 10,000 samples. So here I'm going to say our sample, and I'll just put 1, a sample 1, mean of our sample. I'll put 1s in all of these so I know that it's something very different than the first one. Okay, so this is our new code and it's exactly the same. Now we have a vector of 10,000 spaces, and for every number from 1 to 10,000, our sample 1 is a sample of body temp, 50 people, and our sample 1 at that position is going to be the mean of sample 1. And then we'll make a histogram. Okay, and now it looks much better, much smoother, much more normal. And what's going on is that we didn't really, like 100 samples wasn't enough. So what you might notice is that if we're sampling 50 people each time, then we're sampling with replacement. So there's not enough people for us to make 50 unique samples. So conceptually what we're doing is we're taking out 50 people and then we're putting them back into the population, and then we're taking out another 50 people. This has implications for the generalizations that you can make. Okay, so you'll notice here that even in a sample of 50 people, you'll still get some extreme values, some values that are even over 1 degree more than our average, which is kind of crazy if you think about it. What this means is that we're never 100% confident that something didn't occur just randomly by chance. So the fact that our sample with 50 people can still be an outlier and still be just a matter of chance means we're only ever like 95% confident in our solution, because, you know, there's nothing different about all of these individuals. They are all within the like normal distribution, but a sample of 50 sometimes will still give you these really extreme outliers, which is why we're only ever 95% confident, which is why repeated trials is an essential part of doing science. Okay, so this helps us see how much each sample's mean is different from the overall mean, right? But something that might be more useful to us than like how far is this mean from all the other means is an interval estimate. So the mean of a variable is a point estimate because it's one and only one point. But usually within like the naturally occurring world, it actually makes more sense to report a range of likely values rather than just one and only one value. This range of likely values is the interval estimate. And what this tells us is like any value outside of this range is what is interesting. Like a point value just tells you what the average is, and like one interesting point because it's the point in the middle, the mean. But when you give an interval estimate, you're giving this range of values that are like anything outside of that you can be interested in because it's different. So let's first calculate the confidence interval manually, and then I'll show you how R has some magic tools to let us do that. All right, so we're going to go temp mean, and it's going to be the mean of body temp. Okay, and we're going to go temp standard deviation is going to be the standard deviation of body temp. Body temple is not a thing. Body temp, and remove the NAs. Right, so this says anything that's a null value, just remove it. Obviously not really relevant for our toy data set, but when you're working with a real data set, very relevant. All right, and then our sample size is going to be the length of body temp. So however many values are in body temp. We know this is 10,000, but you don't always know it. Plus, it's easier just to like load it in as a variable. All right, so go ahead and run all that. Our temp mean, we should expect that to be 97.82 or thereabouts. Okay, so we are going to assume a normal distribution, and we are going to use Q norm, which calculates the difference from the mean assuming a normal distribution. Our sample is pretty big, 10,000 is not too bad, so we're going to use a z-score. But if you're talking about samples of like 20 or 50 or like under 100, then you'd use a t-test, and that's something quite different. R calculates this with QT, which you can look up in the documents. I wish that I could tell you like anything above 150 is big and anything under 150 is small, but it's not that clear cut. So it's important to have a good sense of your data. I mean, if you're looking at 10,000, 100,000, those are obviously large. It gets a little bit murkier when you're looking at in the hundreds, so samples in the hundreds. Generally, you'd want to consult a statistician to really figure out what you should do. Big difference is that there's this issue of degrees of freedom, which hopefully we'll cover in class, but is actually not that crucially important for doing data analysis. If you do end up needing it for your project, come and talk to me. Okay, so we are going to calculate this manually. We are going to look for the error. So we're going to call error n, and we will call Q norm and then we want it at 0.975. And we're going to multiply that by the temp standard deviation. Okay, and then we're going to divide it by the square root of the sample size. Okay, so what we're looking at here is 97.5% of the data on the right. I always forget. What this leaves us is 2.5% of the data, which 2.5 on both sides of the tail gives us overall 5%. Okay, so right. No, this is just the total amount of error. All right, so for the left, we're going to calculate, we're going to take the temp mean, and we're going to subtract error n. And then for the right tail, we are going to take the temp mean, and we are going to add error n. Okay? All right, so we are going to run all of this, and what we have here is we're going to call print left n and print right n. Okay, now we'll go ahead and run both of those, and what we see is that the 95%, because we have 97.5 here, so we have 2.5% of the data on either side, either one of the tails, 2.5% here, 2.5% here, looking for our outliers. So we're looking at the 95% in here is from 97.81 to 97.84. So that is our confidence interval. Okay. We're going to skip doing it manually with the t-test because it's actually not quite appropriate for this data set. Okay, you can probably agree with me that this is really annoying and took a lot of time. R has a really handy trick here, and it's confidence interval, body temp, and then we want our confidence to be equal to 0.95. So we'll run that. I got a warning. Oh, that's fine. And what we get here is the exact same numbers. We get the lower confidence interval is 97.811. The upper confidence interval is 97.8385, right? So we have the exact same confidence interval, and it only took us one line of code. There's a similar one for the t-test, which is in the notes, but we're not going to go over it here because it's not quite appropriate. All right. So if we then took all of these measurements we did this at a hospital, right? And we have found that, you know, the range, everyone that we measured at the hospital was like 98.5. Then we can probably be sure that there's some sort of illness going around the hospital, because that is far outside the confidence interval that we would expect. Okay, so the next thing that we're going to do is work with a real data set. So we are going to read in I don't even know how to say his name, but we're going to read in a data set of body temperatures. And this was trying to dispel the myth that 98.6 is like the normal temperature for everyone. Quite interestingly, it's actually not. So let's go ahead and read in the norm temp data set. So we're going to call it real temps. And I'm going to assign real temps to read.csv. And then I think it's on my desktop. And I'll come right back. All right, so hopefully you've downloaded the norm temp data set. We're going to call header equals true. And go ahead and load that in, and then we'll glimpse it. Glimpse of our real temps. And then, so currently gender is being read in as a integer, which is not at all helpful to us. So we are going to call real temps $gender, and we are going to say I want that to be a factor. So as factor real temps $gender. All right, so right now twos and ones are a number, but it actually means something. We have our norm temp readme that tells you which gender is which off the top of my head I'm pretty sure that 2 is female and 1 is male. But let's take a summary to make sure that there are actually ones here. Summary of real temps. And yes, there's ones and there's twos. So there's 130 people. 1 is male, 2 is female. All right, so we're going to make a histogram, and it's going to be hist real temps. And then we want to make a histogram of body temp. We just want to see how this is distributed, you know, if there's any outliers, and there are. There's a couple outliers here, but it looks fairly normally distributed. Not too bad. It's not that many samples, but we can work with it. All right, so we are going to go real mean, and we're going to assign that to the mean of real temps $body temp. Okay, and we'll run that. Okay, and now we'll use our t-test to get the confidence interval here. All right, so we'll call t.test, and we will pass it real mean. We want the body temp because that's what we're trying to model here. Mu is going to be the real mean, and our confidence level that we're looking for is going to be 0.95 because we want 95% confidence. All right, real temps, not real mean. Sorry about that. So there's real temps, not real mean there. Okay, so what we get, our one sample t-test is that our confidence interval is 98.122 to 98.376. So that's the range of values that we would expect, and anything outside of that, like this person that's slightly over 96 or this person that's close to 101, they are outliers. All right, there's a lot more that you can do with this data set, obviously. Go ahead and refer to the data cleaning and manipulation lab in order to work with gender as a factor and get more out of it if you're really interested in body temperatures. Otherwise, this is it for confidence intervals. Go ahead and submit your code here, and I look forward to seeing you in the next lab. All right, bye-bye.